Hi everyone. I'm going to start just a quick recap of moles first. I'm going to try and do paper two or structured questions related to moles. So I have my worksheet open. So we're going to try and see what type of moles questions are going to appear on your paper twos. Now, I'm going to start with the first one, which is let's go with the first theory questions. We're going to start with relative atomic mass. So remember, there's a very high probability of getting this question in your exam. How do you calculate the relative atomic mass? So uh, and it's a very popular question in paper twos. So the first thing is you should know what the formula for AR is. Uh, the relative atomic mass is the average mass of the atom. So what you have to do is you have to calculate the you have to multiply the fractional percentage with your isotopic mass, and you have to sum all of them up. So you multiply it by the isotopic mass, and you take the sum of that. So that's the average of all the isotopes of the atom. So the isotopic mass multiplied by the fractional percentage of that isotope. So for example, over here in this question, if you read this carefully, they're talking about a naturally occurring sample of cerium, which contains only four isotopes. Data for three of the isotopes are shown. So three isotopes they're shown. The fourth one is not shown, and they've told you that the AR of this thing is 140.116. So that's provided, and use this data to calculate the relative isotopic mass of the fourth one. So first thing, remember this that there's a thing called the nucleon number. The nucleon number is the sum of the protons plus the sum of the neutrons, and remember it's always a whole number. It's like if you have 7 protons and 8 neutrons, the nuclear number is going to be 15. So it's always a whole number, and no decimals. Remember not to add any decimals to it. And there's a different thing called the relative isotopic mass, which is almost the same because the proton and the neutron almost have a mass of, or a relative mass of, 1. So but it's not exactly 1. So as you can see over here, if the nuclear number is 140, the isotopic mass is very close to 140 because every proton and every neutron almost has a mass of 1. So if you all add 140 into 1, which is it's going to be something close to 140, but it's not going to be exactly 140 because it's not exactly the mass of a proton. The mass of a neutron is not exactly 138. The mass is very close to 138, but not exactly 138. So remember, mass of the isotope is always in decimals, and it depends on the accuracy of the devices. So we are being asked to calculate the isotopic mass of the fourth one, which we already know that it's going to be something very close to 142, but we're going to try and calculate that one. So first thing is you're going to try and figure out what is the percentage of this isotope. So all the isotopes must add up to 100. So what I'm going to do is I'm going to take 100. That's the total percentage minus the percentage of this isotope, which is 88.45, and then I'm going to subtract 0.251% from that, and then I'm going to subtract 0.185% from that as well. So let's try and do that. I have my calculator with me. So 100 minus 88.45 and minus 0.251. Be careful with your calculators, minus 0.185 as well. So let me just double check. 100 minus 88.45 minus 0.251 and minus 0.185. So it's giving me 11.114%. So this over here is 11.114%, and I don't know what the mass is. So I'm going to take the mass as x, and I'm going to apply the formula. So the average is already given. That's 140.116. And the percentage multiplied by the isotopic mass, that's going to be 0.185 multiplied by, so it's 0.185. That's the first one, divided by 100 into this thing 135.907 plus Percentage, which is 0.251, and that's going to be multiplied by 137.906. And this should be fractional percentage as well. Plus the third one, which is 88.45 into this thing. So that's 88.45 over 100 into 139.905. And the last one is going to be 11.114% over 100 into x, which is the mass of the isotope. So this is this x that we're trying to find. So whenever you're trying to do this question, and this question frequently comes in your paper too. So whenever you're trying to do this question, be very careful with your calculator. So and try and do the working in steps. So take the 100 on the, multiply both sides by 100. So the 100 at the bottom gets cancelled out. So you're left with what's 140, 140 dot 116 into 100. That's 14. This side is 14, 0, 11 dot 6. And I'm going to do the other one, which is point, again, be careful, be 0.185 multiplied by 135.907. The next one is 0.251, and that's being multiplied by 137.906 plus it's 88.45, and that's being multiplied by 139.905. And if I sum that up, that gives me 12.4. So it gives me 12.434 dot 354451. That's what my calculator is giving me. So I'm just writing that down at the moment, and equal to 11 plus 11.114, and that's x. And I'm going to take that to the other side. So this value over here is 140 11.6, and I'm going to minus 12.434 dot 354.451, and I'm going to divide the whole thing by 11.114. And when I do that, I solve this, it's going to come out to be x is equal to 141.915201457. The calculator is giving me a big value. So the decimals are there's three more decimals after that. Now, the question clearly states that the answer should be given up till three decimal places. So you're going to round this off. So make sure don't round off values between while you're doing your calculation, because there's going to be a lot of rounding off error. You're going to avoid that. Make sure try to keep the values as accurate as possible. Try to use the values that your calculator is giving you. Make sure no rounding. Round off when you're writing the answer. The answer should be written in the appropriate significant figures, which over here is already given. That's three decimal places, but usually the rule is that your answer cannot have it cannot be more accurate than the value that's given in the question. Now, so that's one example of a question. Here's another example. They're asking for the definition of the relative atomic mass. So what is the relative atomic mass? It's the average mass of an atom compared to, why is it an average? Because you're calculating the average of the isotopes compared to 1/12 the mass of a carbon 12 isotope. And then he's asking what's the definition of an isotope. It's atoms of the same element having the same proton numbers. but you've got different number of neutrons. Anyway, so they're asking you to calculate the AR in this case. So you're going to use the same formula that X has many different isotopes. So what is the formula? AR is, how do you calculate AR? AR is percentage multiplied by the isotopic mass. So it's going to be 0.89. So 0.89 divided by 100 into 74 plus 9.37 divided by 100 into 76. So the first one, the second one, then you're going to go for the third one, which is what it's 7.60% divided by 100 into 77 plus it's 23.77% over 100 into 78 plus you got 80, not 80 over 100, it's 49. So this one is 49.61 into 80 plus you got 8.73 over 100 into 82. So you got this one and you got this one. So you're going to add all of this up and you'll get your average. Now so we're going to start doing the calculation now. Make sure no errors while you're doing the calculation. So it's I'm going to divide everything by 100 right at the end. So it's going to be 0.89 times 74. Always double check plus 9.37, and that's times 76. And after that, you'll have 7.60 into 77 plus you'll have 23.77 into 78. And make sure you always write your working, because that's very important as well, especially when you're doing paper twos. The presentation of your answer does matter, because you have to impress your examiner. You have to clearly tell your examiner what you're doing. That's how you're going to get marks. Like if you assume that your examiner knows what you're doing, that's going to, I mean, you'll be penalized for that if you don't write this proper steps. Because if you look at any marking scheme, the steps have marks, and marks, they're given marks. So if you don't write those steps, no one really knows how you actually arrived at your answer. So don't assume things. Make sure you write everything, display everything, whatever you're trying to do. So 23.77 into 78, and then you've got 49.61. That's the next one. 49.61 into 80 plus it's 8.73 times 82. And if I divide this by the whole thing by 100, so I'm going to divide the whole thing by 100, and that gives me 79.0421. So the AR comes out to be 79.042 and 1. And did they ask you about this thing in the two decimal places? So you have to round it off till they've asked in the question. So it's going to be 79.04. Now, I got this answer. Make sure you have a way of double checking if your calculator answers are correct. Like even if you look at the graph, you would notice that this has the highest percentage, 80. So your AR is going to be close to 80 or somewhere close to 80. So which you are getting close to 80. So that kind of looks the correct answer in this case. And also be careful that sometimes what they'll do is the total mass or the total percentage would not be out of 100. I mean, over here, make sure. I mean, is this 0.89 out of 100? I mean, what you can do is you can just to double check. Like if you have time at the end, make sure you double check and see if all the percentages they get added up to 100 or not. Because there have been questions where they didn't give it out of 100. So that's and let me see if there is one question similar to that. But anyways, these questions are kind of straightforward. There'll be two questions. We did both types of questions over here. Now moving to the next one, which is also pretty common, especially in your paper twos. Um, and I'm focusing on the big questions at the moment. The ones that carry 10 mark, the 10 mark questions. Usually, you do get 2 3 mark questions here and there, but we're focusing on the big questions. Now, there's another one which is combustion analysis. So let's go to this page, combustion analysis, and we'll try and do a few questions related to combustion analysis. Now remember one thing: when you're doing combustion analysis, um, the question tends to revolve around the fact that for gases, the mole ratio and the volume ratio is exactly the same. What I mean by that is that if I have a reaction where I have only gases and it's forming two NH3, let's assume. So it's one reacting with three to produce two molecules of NH3. Now in gases, the mole ratio and volume ratio is exactly the same. So if I have 10,000 cm cube of N2, then automatically I don't need to do any calculations. 1:3. So the amount of hydrogen gas that is going to be used up in the reaction is going to be 30,000 cm cube. And the amount of ammonia that's going to be produced is going to be 20,000 cm cube. So it's kind of understood that uh, that you don't have to do calculation. Mole ratio and volume ratio for gases is exactly the same. Now, if you look at this question, and here's a combustion analysis question. By looking or analyzing the combustion products, you will be able to figure out the structure of or the formula of this molecule over here. So we've got an alcohol, and the alcohol T occupies a volume of 20 cm cube. So we found this one is occupying a volume of 20 cm cube, and at 120 centigrade and 100 kilopascals, the sample was completely burned in 200 cm cube of excess oxygen. So the amount of oxygen is 200 cm cube, but remember it's in excess. So that means it's not 200 cm cube that's actually taking part in the reaction. It's probably going to be less than 200 cm cube. So not exactly 200 cm cube. The final volume measured under the same conditions as the gaseous sample was 250 cm cube. So now he says when the combustion happens, the final volume that you have is coming out to be 250. It's coming out to be 250 cm cube. Uh, that's your that's your final volume. Uh, so what does the and the final volume is being obtained at under these conditions. All water is vaporized. Uh, so that means water is in the form of vapor. So what does this 250 cm cube contain? This 250 cm cube has your products. It's got this carbon dioxide, which is in gaseous state, and it's also got water vapors, which are in gaseous state. Why are they in gaseous state? Because they told us that the temperature is 120 centigrade. So water at 120 is going to be a gas. So that's my final volume. What else does the final volume contain? It also contains the leftover oxygen, because oxygen, remember, is in excess. So the alcohol would have completely reacted, but some of the oxygen would be. So there is some oxygen present as well. He now then says that if you remove the water vapor from the gaseous mixture, decreases to 170. So if you get rid of the water vapor, so now your volume is from 270 cm cube, it's now 170 cm cube. So basically now you have carbon dioxide and oxygen gas only. So you remove water. So how much was water? Water was with water the volume was 250, and without water the volume is 170. So water had a volume of 80 centimeter cube. The question then goes on to state that if you remove by passing the gas through concentrated alkali and you absorb the carbon dioxide as well, the volume further decreases to 110 cm cube. So now what happens is you remove CO2 So now the only thing that's left is O2. So the volume decreases to 110 cm cube. So how much CO2 was removed? It's you started off with 170, remove CO2, and volume decreases to 110. So the amount of CO2 that's going to be not 70, it's going to be 60 cm cube. So it's going to be 60 cm cube. So what I've now figured out based on this is that I know that the amount of water vapors that I had was it was 80 cm cube, and I know for a fact that the amount of CO2 that I have in this reaction, that's 60 cm cube. I also know the amount of O2 that got used up because you started off with 200 cm cube, and now at the end you're left with 110 cm cube. So that means 90 cm cube actually took part in the reaction. And your starting point was that so is I hopefully is this clear? This is clear to everyone that you started off at 200 cm cube, 110 is still left at the end. So only 90 is reacting, and the alcohol, that's 20 cm cube. Now remember, mole ratio and volume ratio is exactly the same. So what I'm going to do is I'm going to convert this into a whole number ratio. So mole ratio and volume ratio is exactly the same. So if I convert the volume ratio into a whole number ratio, this would be 1. This is going to be 4.5. This is going to be 3. And this is going to be 4H2O. So what that means is that one molecule would react with 4.5 O2. So if it's reacting with 4.5 O2, that means Z has a value of 4.5. And one molecule reacts with 3 CO2. So that means X has a value of 3. And one molecule is reacting with 4 H2Os. So that means Y by 2 has a value of, it's got a value of 4. So that translates to Y having a value of 8. So my formula, which was CXHY and O, is actually in fact X is 3 and H is 8 and O is, I mean, O was already 1. We already knew that. So that's how you're going to figure out the formula of a compound. That if you know the volume ratio, you can figure out the mole ratio. If you know the mole ratio, all you have to do is you have to do a simple comparison. But keep the first one as 1 mole because the equation states 1 mole is reacting. So when you do the ratio, make sure the first one is 1 mole. So 1 mole reacts with 4.5, so Z is 4.5, X is 3, and Y by 2 is 4. Now we're going to try and do another simple question, which is kind of very simple. This time he says there is P, which is CXHY, and there's 25 cm cube of it. So let's try and do that. That's 25 cm cube. And it's reacting with 200 cm cube of oxygen. So, and let me, so it's 25 cm cube that's reacting with 200 cm cube again. And again, they say that it's in excess. And then the final volume measured under the same condition as the gaseous sample so that the water produces liquid was 150. So the final volume is, and the final volume of gas, they're talking about the gas. The final volume of gas is given as 150 cm cube. So at 37 degrees centigrade, what are the gases that are produced? This CO2 gas that's produced. So this volume contains CO2. Water is going to be a liquid. They already told us that 37. They already told us over here that water is a liquid, so it's not a gas. So that means your product only has one gas, which is CO2. So 150 cm cube of CO2 plus the leftover oxygen, the excess oxygen. So plus your excess O2. Now you got this, and now you have. They say that treating the remaining gaseous mixture with concentrated alkali to absorb the carbon dioxide. So when they absorbed, CO2, the volume decreases to 50 cm cube. So the volume, So the volume decreases to 50 cm cube, and it no longer has carbon dioxide. So that means the amount of carbon dioxide was 100 cm cube. So the amount of carbon dioxide is going to be 100 cm cube, and there's going to be 50 cm cube of leftover O2. So that means the amount of oxygen that actually got used up was 150, because at the end you still have 50 cm cube that's left, that is unreacted. So I've figured this out. I can turn this into volume ratio and mole ratio are exactly the same. So 25 ratio 150 ratio 100. What ratio is that? If I divide everything by 25, that's going to be 1. This divided by 25 would, I think, give you 6. And this divided by 25 would give you 4. So that means one molecule reacts with 4 CO2. So that gives X as being equal to 4. And one molecule reacts with 6 O2. So that means X plus Y by 4 is 6. And we already know X. So that's 4. If I get the 4 to the other side, that's becoming 2. And Y would come out to be 8. So the formula is C4 and H8. So that's going to be my formula for this one. And just hold on 1 second. So it's going to be C4H8. And you're going to get plenty of questions. They're even going to ask you to balance this equation. So remember this general equation for gas combustion. You have to memorize this as well. It's X carbon dioxides and Y by 2 water molecules. But the questions are kind of pretty standard. And uh, I mean, if we do this quickly, you got 10 cm cube of A. This is A. And that is burnt. So this one is 10 cm cube. And it's burnt with 50 cm cube excess oxygen. So remember, 50 cm cube excess, 40 cm cube of gas remained after cooling the apparatus to room temperature. So the 40 cm cube of gas that remains, what does that? It contains your product, which is CO2. So it's got CO2. Water is a liquid. Remember, room temperature. They're talking about room temperature, so water is a liquid. So the only gas in that 40 cm cube is going to be CO2, and the leftover oxygen. And then the 40 cm cube was shaken with an excess of potassium hydroxide. Remember, alkalis, they absorb carbon dioxide, so 30 cm cube of gas remained. So when you absorbed CO2, you're left with 30 cm cube of gas. So how much CO2 is present? That's 10 cm cube, because you had 40 and you absorbed carbon dioxide. The volume decreases to 30. So that means you just have 10 cm cube, and the leftover 30 cm cube, that's your oxygen gas. So we're going to plug all those values in. This is the amount of carbon dioxide that's being produced is 10 cm cube, and the amount of oxygen that got used up, you added 50, and the question states that at the end 30 cm cube is still remaining. So that means only 20 is actually taking part in the reaction. So what's the whole number ratio? It's going to be 1 ratio 2 ratio 1. So X will have a value of 1. One molecule produces 1 of this, and X plus Y by 4 has a value of 2. I mean, this whole coefficient is 2. It's one molecule reacts with 2 O2s, and I'm going to plug in X over here. If I do that, Y would come out to be equal to 4. So this thing is actually CH4. So ये ठीक है. It's how you're going to try and do this one. Now let me just go back. So here are two main types of questions. I'm going to the other ones. The ones that are more important. There are also big questions on that. that would come in your exams. They are related to, where's my, one second. So these ones, they're mostly related to titration. So we're going to do titration questions, but I'll do that in the next session for this, which will happen very very quickly. So I'm going to do a couple of titration questions. So remember, big questions. Big questions in paper twos would be coming from relative atomic mass, or they would be coming from combustion analysis, or they would be coming from titration. The other ones, you'll get smaller, simpler moles questions. So I'll try and do the other ones in the titration one.